Without more something limited. It's my pleasure to introduce the main speaker this morning. And today has been very, very influential here at the intersection of large process, differential calculus, with meshing systems, columns, scalar vector fields, and more usually multiple geometry. All of that is associated with this output of the shape. And years ago, I believe back to how Paris and also you can use this one. Also, you can this one. We can change. This workshop. Thank you so much, Jorgen. Thank you for no. How do I turn it off? Okay. Thank you to the organizers of SPM and SMI to invite me. Turkey was one of the few countries that I haven't visited yet, so I'm delighted to be here. And I'm delighted to speak with geometric and simulation type of colleagues so that I can really talk about my research without trying to, be super soft in the way I present things. So I apologize if I go a little bit fast, but because I'm talking to experts, I'm going to go to town. And I promise you all that I will neither use Bézier nor de Casteljon, which I guess I already lost my bet right there, but there will be no mention of these two names in my talks. Okay, so like Jörg said, I will try to explain what I mean by computing through the lens of geometry. So you all know geometry. Obviously, it's been key in many scientific fields. In particular, one could say that I think our ancestors really looked at the world around them and saw that there were some invariants and symmetries in the world. And that's what led to geometry being really the mother tongue of some of the most influential physical theories, all the way to general relativity. Otherwise, I'm not going to talk about GR today, but it's been very influential with lots of great names that are associated with the field, obviously. But obviously, these people, and I cannot hold this against them, they didn't have computers. So they did pretty much everything with pen and paper, right? And so when I started looking into it, now to use this on a computer, so that when what we talk about a surface, it's actually either a triangle mesh or point set, or etc., but something discrete. All of the notions that were defined by all these fantastic people do not really apply directly, right? And so this is the tension that I've been facing all my life, how to go from the continuum world to more like a finitude, meaning discrete sets of primitives to define a surface. And this is why I've been working a lot on this notion of discrete differential geometry, where really we're thinking about a finite dimensional counterpart to the continuous theory. That's what really it's all about. And we are actually leveraging a lot some of the differential understanding that people have accumulated, and we use this for our discrete computation. So really, I think of geometry as a guiding principle if you want to know how to discretize things. That's what I call the lens of geometry. And in fact, it's been proven many, many times over, I will mention a few examples, that if you discretize the geometric principles, you will get predictive power in your computations. Whereas if you try to discretize the PDEs or the results of these principles directly, you're going to have to guess how to discretize things. And most of the time, you will not find a good discretization. So an example of that I like to give, but now it's so dated that I will not explain it. But if you know about the mean curvature flow, you know that you can move a surface so that it's moving basically along the normal. Sorry, I'm still learning how to do this after 25 years of academia. Okay, cannot find the button. So, all right. You want to move along the normal to the surface and proportional to the mean curvature h of the surface. If you can tell me, I would be great. It's on the side. Oh, okay, this one. Thank you. So this normal, maybe you can on a discrete mesh, maybe it's not too hard to compute, but the mean curvature, that's already much harder. And so people have debated how to do this. But again, if you go back to the differential understanding of this curvature, mean curvature flow, you know that it's actually a gradient of the area, basically. It's the direction towards you should move if you want to reduce the area of your mesh as fast as possible. And so in that case, because a triangle mesh is, a bunch of triangles, we know how to compute the gradient, the exact gradient of an area with respect to a vertex. We can actually do this mean curvature flow without even thinking really too much about these discrete entities. Another example was with more in the animation arena. Back in the days when we were trying to do shells, every physics paper were using at least quadratic order basis functions to do simulations of shells. So when we came up with a way to do this on piecewise linear basis functions, people basically thought that we were crazy. That was heresy. That was considered heresy because there was just not enough derivatives to capture shells. Well, long story short, it does work. That's what all these discrete rods and discrete shells are based upon. So at least that proves some people wrong. And there is interest, of course, in academia, but also lots of interesting application that I had the pleasure of doing over the years. But what I really like about discrete differential geometry is that it's very good for educational purposes because it presents really very clear analogs in the discrete world of fairly complex, sometimes continuous notions. So it's easier to explain with a triangle mesh than a smooth manifold. It's always good to make also pretty pictures and fast animation in the context of Hollywood movies or anything. So that's always fun. And also from the computational science point of view, we get to do from time to time some new numerical schemes really based on this lens of geometry. So that has been the three most rewarding experiences that I've had. And today, just to sort of recap a little bit of this, I'm going to show you four vignettes of different types of work. Hopefully, they will illustrate all this in four sort of distinct cases. And let's start right away. So the first one is related actually to what Jörg was talking about, this notion of how to do calculus on meshes, because after all, we need to do some kind of computation on meshes. So how do you do this? So I always like to give this example. I usually use this slide in the fall because then sometimes I can celebrate the anniversary. Like last year, I got to almost celebrate its anniversary exactly on the day. But Leibniz wrote this sentence, which basically says it will be useful to use the integral sign to replace omnia. Omnia means for all, like the sum over all the indices, if you want. And that was the first time that really people went from discrete interpretation of formulas where there was sum of infinite small numbers to the notion of integral. And of course, that was very easy to manipulate with pen and paper, paper, pen and paper. That's interesting. Pen and paper. And fast forward to now, we have computers, and so now we need to go back to the discrete way of thinking about integrals, right? So there's an interesting back and forth between continuous and discrete, which is right on this discrete differential geometry point of view. So when I started working on how to do calculus on meshes, it was clear to me that by looking at a mesh, at least the notion of differential or geometric quantities were discrete in the sense that they live at very special places. So if you take, for instance, a piecewise linear surface, a bunch of triangles, let's say, then you'll see that each triangle is flat. So there's no notion of curvature inside a triangle, right? It's perfectly flat. But now if you look between two triangles, clearly there is a mean curvature. If you remember that in the continuous world, the two principal curvatures, there's a maximum and a minimum that are supposed to be at right angle from each other. Well, clearly along the edge, you have a zero curvature along the edge, and then a maximum curvature or minimum curvature if it's negative between the two triangles, right? The dihedral angle between the two triangles. So clearly, mean curvature somehow lives just at edges. So you can think of them as sort of distributions, like a Dirac along the edge, right? Same thing, of course, for the Gaussian curvature. If you also know that Gaussian curvature is supposed to be zero for a developable surface, that means that two triangles join with their common edge will have a zero Gaussian curvature because you can always open them to become flat, right? So there is no Gaussian curvature along the edges. But at vertices now, there's clearly something that can happen, which will be if your local one ring is not flat, or not developable, the Gaussian curvature will not be zero. So clearly, there's also a Dirac right there on the vertex. And when you talk about distribution for computational purposes, clearly you need to integrate them, right? So that you can get numbers, just numbers on those edges and nodes, etc. And so that calls for integration. And integration, if you ask a mathematician or a geometer, they will tell you that the tool to proceed with integration is the notion of differential forms, which is really just an anti-symmetric tensor. This is the object that really begs to be integrated. So this is the f of x dx when you see this kind of integral. This is not in the geometric context, but you've seen this type of integral before. The dx really is the one form in this case that you integrate. But very often at the time when I started, it was not used for computation, this notion of forms. And yet we know that integration is naturally good for computation, right? It's even robust to nodes. So it struck me as something that was underutilized and underappreciated. However, I was a little bit stuck because I didn't have the words to create such a mathematical framework. So thank God one of my colleagues, Jerry Marsden, pointed me to exterior calculus, which is really a very nice piece of work done by Cartan and people before him to extend the notion of divergence, curl, and grad on non-flat domains. And again, Cartan made this exterior calculus really a calculus based on differential forms, these anti-symmetric tensors that I talked about right before. And so now, as I told you, a k-dimensional form wants to be integrated on a k-dimensional domain. That's why it's the k basically indicates the size of the dimension of the domain. And these differential forms are very nice because, well, they are geometric in the sense that you don't need to be encumbered by coordinate systems. You can actually express them without really a coordinate system. Of course, you can use also a coordinate system, but you don't need it. For instance, when you're dealing with a flux, the notion of flux is a very physical notion, right? You know that if you have a quantity that is a flux, well, then if you have a phase, you know how to compute the flux through the phase fairly easily. And in fact, this exterior calculus is really the basis of all modern differential geometry, including Hodge theory. And it's very nice because it really separates topology from metric, which again, for meshes is nice. It's nice to separate what's topological and what really requires length and dimensions, basically. And it turns out that it's only based out of 7 basic operators. So that seems like a feasible thing to discretize. So we did this. That's called discrete exterior calculus. Basically, like I said, we use the mesh as a computational structure. So we store the, so we see, first of all, the simplices of a triangle mesh, let's say. It has been extended to non-simplicial meshes, but let me stick to simplicial meshes. So we see all of the simplices as basically entities, and we can create chains. Chains will be just linear combinations of those simplices. And then from this domain, if you want, the chains represent sort of a domain, we can store now k-dimensional forms by just integrating a continuous form on those simplices, because the mesh, if you want, is a bunch of very well-defined small domains. So now we can integrate, for instance, a two form on a triangle. We can integrate a zero form on a vertex, etc. So we call sometimes these discrete forms cochains because they are the dual, if you want, of the notion of chains. And so now complicated notions like the D, which is the exterior derivative in exterior calculus, can be actually done quite easily by basically using Stokes. If you have heard about Stokes' theorem, this is basically saying that the integral of the differential of a form omega over a domain is nothing but the integral of omega itself over the boundary of the domain. This is called sometimes, divergence theorem. I mean, there's plenty of names. Stokes is the general phrasing of all this theorem. So it turns out that here you can see that the D basically is equivalent through adjointness to a boundary operator. The boundary of a simplex, we know how to compute this. So guess what? That means that you immediately know how to compute D because you have a well-defined boundary on your meshes. And by the way, because of this definition, D is purely topological. You don't need to know the size of a triangle sigma, for instance, to perform this Stokes theorem. So this is what I was talking about, separating topology from metric. And that leads to plenty of things like homology, cohomology. I'm not going to go through the details, but once you have this kind of notion, then all the continuous notions go through, basically. And same thing for the Hodge star. The Hodge star is also a very interesting operator for exterior calculus. And here, if you don't mind having a low order Hodge star, there's a very nice duality between the primal and dual of a mesh that can be used to compute a low accurate but extremely versatile Hodge star on meshes too. And then from this, you can assemble what we call the de Rham complex. So it's, if you're not aware of it, it's a little bit complicated, but basically this is the discrete version of this. So you store scalar values on either nodes or tets. Let's say this is for 3D. So nodes or tets are used to store scalar values. Really, this is more like a density value instead of scalar value, but basically it's the same thing. And then you can take gradients of a function on nodes that will give you a function on edges, I mean, values on edges, and you can take the curl of the edges to give you a value on faces, etc. So all of this satisfied the normal exterior calculus point of view, but now completely discretized on a simplified mesh. That's why it's nice. And it turns out to be basically just a simple exercise in matrix assembly when you understand it properly. So that means, for instance, you can do Hodge theory directly on triangle meshes. All the notion of harmonic forms, cohomology, all of this carries through intact. You can even do finite element by using Whitney basis function, not just associated with nodes, but also associated with edges, like finite elements associated with edges and facets and etc. So that's quite powerful. And you can even, if you're not happy with the piecewise linear accuracy, meaning first order accuracy, you can go to higher order accuracy using subdivision or even spectral basis. So I'm not going to bore you with the details, but with this, you can do lots of application all the way from Hodge decomposition in all of its glory, 5-term components. Decomposition, sorry. You can do plenty of geometry processing all the way from parametrization to geodesics to even masonry. And you can even do animation. So we use actually this deck point of view to basically make sure that vorticity is really advected in a domain, in the 3D domain to simulate Navier-Stokes properly. Okay, so this is the most abstract part of my talk. Now let me go to something much more practical, although underneath it all, there is still the same level of, we're trying to make sure that what we do exactly mirror the continuous world, right? This is the good thing about discrete differential geometry. We really try to mirror the continuous world. In effect, we're not inventing anything. We're just explaining how to adapt this continuous thing to the discrete world. So the second part is about grooming. So grooming, if you don't know about it, it's how to grow feathers or hair on digital characters. So for instance, if you take Remy, the little rat from Ratatouille, you can imagine that no animator or no artist that is still alive, at least, has taken time to enter all the hair by hand, right? This is not possible. So how do you do this? You basically define a vector field on the surface of the rat, and then you will grow the hair along the vector field. So that asks the question, how do you design a vector field on a non-smooth surface? So that leads us to this notion of vector field processing. And of course, when I say vector field, could be actually direction field. Sometimes the magnitude does not matter. For instance, for hair, magnitude is not really important. It's the direction towards which you want to grow the hair that matters. It can be also frame field. I'm not going to talk about all this. I'm just going to stick to direction field today because that's simpler to explain. And we wanted to provide notions for artists to be able to design some kind of a vector field like this, where they can control where the maelstroms, where the singularities, if you want, of the vector field appear, right? Because if you think about hair, either the hair of on somebody's head or for the rat, clearly there are spots within the vector field that are more salient, more visually striking than others. For instance, a bald spot where the vector field goes to zero, basically, or where there's a singularity, if you want, will be very visible. And the artists really want to put these singularities at particular places, sometimes hidden places, or sometimes very visual, very obvious places, so that it looks in a very particular way. So we wanted the artist to have control over both the smoothness of the vector field, but also the placement of the singularities. And to do this, there were plenty of methods because we have a very healthy geometry processing community. So there was lots of great ideas. But we actually decided to use another tool, which was connections. Connections, if you want, is one step further from exterior calculus in the sense that now you're trying to talk about parallel transport of vector field on surfaces. So this is what a connection one form is about, is basically how do you define the notion of parallel transport on a triangle mesh. So it turns out that it's actually not that hard. And again, we're going to rely on this very simple pair of triangle idea. And between a pair of triangle, you can think of the edge in between as a hinge, right? Like the hinge of a door. And here is how we proceed with parallel transport. It's very easy. Imagine first that you store a vector, a blue vector here in one of the two triangles. This vector, somebody give it to you. And you're being tasked to actually parallel transport this vector to the other triangle over. So parallel transport, you know, when you're in the plane, parallel transport is trivial. It's just translation. But on a non-smooth surface, lots of geometers thought about what is the right way to think about parallel transport. But here for triangles, there's a very simple way. I told you, actually, I alluded to it a little bit earlier. When you have two triangles, you can always flatten the hinge between the two triangles without deforming the triangles, to make them flat, to make them live in the same plane. Once you do this, you are in the same plane. So you can just translate the blue vector to the other triangle, no problem. It's a plane, it's just a translation. And then you fold it back. That's all you have to do, right? So conceptually, parallel transport, at least this notion that I just explained, is really trivial. Now, of course, this is a conceptual idea. It doesn't tell you how to code this up, okay? And most of you are interested in how to code this kind of things up, so let me explain. Basically, for every edge between two triangles, let's say triangle I and J, you're going to store just one angle that explains the change of bases between triangle I and triangle J. So how does it work? Basically, you start from all the triangles of your mesh, you assign a coordinate system, two-dimensional coordinate system inside each triangle. You can pick whatever you want. Typically, people will pick coordinate systems that are aligned with one of the edges. But again, you can do whatever you want, just random assignment of coordinate frames on each triangle. You just need to remember what you did when you define them. And then the number that I alluded to, the angle between the two edges, is simply the smallest angle that you need to rotate one frame from I to the frame in J. Okay? This angle basically tells you what type of rotation do you need to go from the frame in I to the frame in J. And of course, I lives in its own tangent plane, meaning the first triangle, and J lives in its own tangent plane, meaning the triangle J. But the rotation is to tell you how the two frames are related. Again, thought of as living in the same plane because you flatten the hinge map in the plane. Okay, so that means that, oh, basically, why is this an implementation of this? Because now, if you know the two coordinates A and B, or X and Y, sorry, or U and V, I guess, U and V coordinate of this guy in this frame, you will know exactly the coordinate U and V of the parallel transported vector in that frame by just hitting the UV coordinates by the rotation by the small angle alpha. That's it. So this gives you a concrete numerical way to perform this conceptual parallel transport. And it turns out that it's not hard to see or to prove that this notion of parallel transport is nothing but the Levi-Civita metric connection one form. So basically, it's a very natural connection that, guess what, geometers have found way before we started thinking about triangle meshes. And in fact, all the notions of Levi-Civita already show up even on triangle meshes. For instance, if you have a non-flat one ring and you start with one triangle, you parallel transport it around the vertex in a loop. If you want around the vertex, you will see that you will not come back to the same vector. And that's called holonomy. It's basically the mismatch that you have when you do a little loop, a parallel transport around a little loop. If locally you're not flat, you're going to not get the same angle. And again, geometer proved that this difference of angle is nothing but the integral of the Gaussian curvature if you use the Levi-Civita connection. The integral of the Gaussian curvature over this region that is bounded by the little curve. So, by the way, that means that you now know the the discrete Gaussian curvature for a triangle mesh is nothing but this angle, which turns out to be 2 pi minus the sum of the tip angles. That's not a very difficult derivation. Okay, so we have defined a notion of Levi-Civita connection. Turns out that Levi-Civita is just one particular type of connection, but you can actually extend it to any principal connection. What you simply do is, instead of doing this very naive or very canonical way of doing parallel transport, instead of just doing one single translation here from this vector to this vector, you add also a tiny adjustment, a tiny rotation. Okay, so this is not the same angle as this guy. This angle was to really define the Levi-Civita. Here I'm just saying from the Levi-Civita, if you add another adjustment rotation between two triangles, you're changing the notion of connection. And again, this is something that people know very well in the continuous world, because Levi-Civita, again, is just one particular case of connection one form, but you can come up with as many as you want. And so going back to the problem of designing vector fields such that you control exactly where the singularities are, etc., we had the idea now that, hey, now that we have this notion of parallel transport, could we compute these little adjustment rotations that I just defined between two adjacent triangles who have a little degree of freedom, this adjustment rotation? Could we make them such that the holonomy that we had initially, remember the Levi-Civita connection? When you were doing a little parallel transport around the vertex, you were not getting back to the same triangle. What about we mess up with the Levi-Civita with this extra rotation, adjustment rotation, such that now on all the little loop, the holonomy is 0, meaning that you're guaranteed that when you do parallel transport, you come back to the exact same place. Well, it turns out that you can actually do this if you count the number of unknowns, because we have this little adjustment angle that you have on every pair of triangles. If you look at this counting compared to the number of little loops that you can do on a mesh, you realize that there's more little adjustment than number of loops. So you can always kill the holonomy almost everywhere. And I say almost everywhere because math is still there to annoy you. There is, again, in the continuous world, something that is well known as the Poincaré-Hopf theorem that tells you basically that somehow the curvature that you kill by changing the holonomy to 0 has to go somewhere. You cannot kill it everywhere because that would mean that your surface is suddenly magically flat. It was not flat, it was a curved surface. So you have at least one singularity that has to be somewhere, or multiple ones if you prefer. Again, you let this handled by the animator where he wants or where she wants the singularities. And once you know this, I told you that there's always plenty of adjustment angles that you can pick. what we recommended in one of our papers was to find the smallest adjustment vector, meaning the L2 minimum of all the possible adjustment angles. I don't know why I put vectors, it's angles here. So that you don't deviate too much from the Levi-Civita connection while killing the holonomy almost everywhere except at singularities. And so what this creates, yeah, by the way, recently we realized that this notion of smallest actually meant that we were minimizing the torsion. So at the time, we didn't know that it was actually torsion of the connection. So if you want to understand why it is, go back to a SIGGRAPH paper from last year, but this is irrelevant to my discussion here. So now that you have these adjustment angles that are particularly picked so that they kill the holonomy of the Levi-Civita, that means that now you can start from one vector in one triangle of your mesh anywhere, and you can parallel transport it in any direction that you want, in any order that you want, because you will get a completely smooth vector field. Because there will be no disagreement whether you turn left or you turn right, you will get back to the same value. So you can do really a propagation over the whole mesh, and you'll get a vector field, a direction field on your mesh. And because it's super close to the Levi-Civita, because you pick the smallest adjustment, it will be very smooth. And because it's exactly kills the holonomy everywhere except at the singularities, it guarantees that the singularities that you picked, the vertices that you picked to be the singularities, that's where your vector field will have a singularity and nowhere else. So that means that, for instance, for this bunny, if the artist picks those places for the singularities, for whatever reason, they will get with just one single linear system of a very sparse matrix, so it's super fast. You will get what we call a trivial connection because it's a connection with almost zero curvature everywhere. That defines a vector field the way the artist wanted, with exactly the right placement of singularities. And of course, there was no singularity in the back, and you see that the solution has no singularity indeed. So it really respects exactly the singularity. And it turns out also that this is very robust to the meshing quality. So if you have very nice and fine triangles here, it gives one result. If you have messy triangles with very badly shaped triangles here, or a refined set of triangles here, for instance, it still gives you visually the same vector field, basically. And so now if you give this to animators, and we gave this to Pixar animators, well, they have fun with this. So for instance, this character is entirely done, even the feathers is done with this method. And so when you work with Pixar, that's good, you get little trailers. So to present our paper, they gave us this little trailer using our technique. Okay, so this grooming project was nice, but then we said, okay, we've been grooming horses. Can we groom also data? Meaning, can we use it for other applications, not in 3D, because 3D can be boring? Can we go to higher dimension? And it turns out that, to my surprise, it did work almost exactly like grooming, but now for data science. So let me explain the problem that we found that's required the same type of math to solve it. It's called dimensionality reduction. I'm sure you've heard about it. You know that if you have a data set where every point of your data set lives in a super high dimensional space, let's say r to the power big T, where T is really large, and you want somehow to project it to a small dimension, right? Let's say a Euclidean space of dimension little t now, where little t is much smaller than big T. So basically, you want to try to find a Euclidean embedding of your high dimensional space now into low dimension. And of course, there's plenty of this. You can just pick random assignments, but that's not good. You want, in a way, to make this in the most isometric way possible, meaning that the distances that was in r to the power big T should be proportional to the distances that you have in r to the power little t, meaning that the points should be relative to each other still the same way they were. So you try to do a projection for high dimension to low dimension where the vicinity notion between points stays the same. Here's an example for a particularly large big D, which is 3, and a particularly small little d, which is 2. Okay, just to get the idea more obvious. So if you see this little piece of rolled cheese or whatever you want to call it, a little ribbon, you want to unfold it into 2D without changing the distances between pairwise of points inside the ribbon, right? So you really do an unfolding like this. And it turns out that people call this nonlinear dimensionality reduction because, of course, you know of other ways of doing dimensionality reduction. You know, PCA, for instance, right? Principal component analysis is a way to do dimensionality reduction. But if you apply it to this guy, it will just project the ribbon flat, which is not what you want. Here, you want to uncurl it, unfurl it, and unfold it flat. That's why it's a nonlinear dimensionality reduction. And it turns out that people have done this already, all based in eigenanalysis. There's plenty of methods. There's a method that's called isomap that takes the pair of all the geodesic distances between your data set, your data points, and then from this big matrix of all the distances between every pair of points, they find an embedding in a low dimension. And this one is most probably the one that is used the most because it's very robust to noise, because you really take into account every distances, basically every pair of distances. And then there have been methods that are much more economical in the sense that they only look at your direct neighbors. The problem is, and there's a huge amount of them, from Laplacian embeddings to locally linear embedding, etc. The problem is that they become very brittle. So this method works great if you have data that has no noise. As soon as you add a little bit of noise, it just collapses. So that's why in practice, people prefer isomap. And it's been really hailed as a great extension of PCA because it does basically nonlinear dimensionality reduction for just basically a big eigen analysis of this distance matrix of the geodesic distances. So how does it do it? Without getting into the details, like I said, you want all the geodesic distance between your point in high dimension. So what do? Basically, from all your points, you create some kind of a graph of nearest neighbors. So for every point, you link it to its k nearest neighbors, where k is small. That creates a whole graph of your data. Then on this graph, you run Dijkstra's algorithm to compute all the pairwise distances. That will be your approximation of the geodesic distances. So basically, you perform a Dijkstra approximation of the geodesic distances on this k-nearest graph, k-nearest neighbor graph. And then from this matrix of all the distances, there's a very nice mathematical tool that I will not discuss, but a very simple, it's called multi-dimensional scaling, a very simple eigenanalysis of this matrix that tells you exactly how to map it after that into low dimension so that the isometry is as good as possible. So this part is exact. In a way, it's the optimal way mathematically to do it for a particular notion of isometry. But this part is actually really bad. The Dijkstra algorithm, I never really realized until we got into this project how bad it could be. And here is why I'm saying it's bad. And I hope that your geometer brain will react as strongly as I did when I first saw this. So if you take even points that lie in a 2D plane in 3D, and you ask for this isomap to project it into 2D, you would expect that the projections should be perfect, right? I mean, it's a flat bunch of points. Actually, it's not. So that means that in this particular case, where PCA will give you obviously exactly the right answer, isomap is much worse. They get like up to 5% of inaccuracies, whereas PCA is exact. So that was the first sort of surprise. And why, by the way? Because Dijkstra, of course, it uses the graph as a way to estimate distances. So as the graph never goes straight, you overestimate, in a sense, all the distances. And so when you ask to project after that, obviously there's going to be errors. Then if you give a bunch of points that are on a developable surface, I would say as a geometer, I would hope that they do a pretty good job. And again, it can go widely wrong if you use this isomap. And finally, if you have even a hole in your data, like this big hole in this ribbon, then the hole gets completely magnified. Again, why? Because in the Dijkstra algorithm, to compute the distance between this point and this point, it has to go around the hole. And so the distance is in a way messed up by the presence of the hole. Then if you think about it, this is a big hole, obviously, but between any 2 points, there's a hole too. We're talking about samples. So there's holes everywhere. That's why even for the flat case, you always will have errors. And so we decided that because Dijkstra is the root of all evil in ISOMAP, why don't we try to change it? And it turns out by using exactly the same ideas as the trivial connection example for grooming that I told you about, we can actually fix it. So I'm not going to go through the details, but basically we start the same way. We start with k-nearest neighbors, but now from the k-nearest neighbors, we estimate a tangent plane, a little bit like the triangle before. So we have, for every point, we have a plane, just like the triangle before. And then now for two neighboring planes, we compute the equivalent of the matrix, I mean, the angle that was the angle of the Levi-Civita connection, how to move from one coordinate frame to the next. So here we do the same thing. For every plane, we assign a random coordinate system. And then we find the matrix that will bring you one coordinate system to the neighboring coordinate system. This is exactly a connection too, but now in high dimension. But otherwise, exactly like it before, and it turns out that there is a closed form solution from this through a simple SVD, so no complication. And then we can actually evaluate the geodesic distances much more accurately than Dijkstra using something called Cartan's development. Not going to go through the details, but basically what it does the parallel transport of the curve of the path between 2 points. So if you think about one point I going to this point IM, I1 to IM, if you do the parallel transport of the curve into the tangent plane at I1, you see a curve like this. And now if I'm asking you what is the distance between I1 and IM, Dijkstra will just sum all these little distances here. But with this Cartan development, you actually know that a much better estimate of the distance is simply from this point to this point. Why? Because in Cartan's development, this parallel transport idea of curves, it turns out that a geodesic is actually a straight line. So if you want the geodesic distance between this guy and this guy, just take a straight line in between. So by doing this, you remove all the zigzagging that Dijkstra does or the going around a hole to get to the other guy. Here you can cut through and avoid the inaccuracy of your geodesic distances. And so by changing now 6 lines basically on the ISOMAP code, you can now, for instance, get the hole inside this S to be the normal hole. And unlike the original example, it turns out, okay, I'm showing you 3D examples of like 4, how to call this? Petals of a rose kind of thing that should project into petals, but when you use ISOMAP, it's completely degenerate, whereas ours keep the shape of these petals. And you can even try it with real images. I told you that you can consider these points in high dimensional space to be, for instance, images. So this is a 64 by 64 or maybe 128 by 128 picture of an A. And you see that the A has different scales and different rotations. And again, by sending randomly the images of the A to ISOMAP, ISOMAP can sort them out based on scaling and rotation. So it's very nice. It turns out that our method does something very similar in this case, so it's hard to argue that we're better than ISOMAP. But what we did after that, we took the ISOMAP results, we removed a bunch of the images that were all this point here, all these red points in this region. For us, no problem. We just find basically the same embedding with just the missing images missing. Whereas ISOMAP get completely confused, right? Because now Dijkstra will have to go through the hole and you mess up entirely all the dimension. So that shows you how much more stable you are with this. Okay, so for my third vignette, I go to something very different. Again, the SPM crowd, we enjoy it to have a little bit mechanics or simulation in all this. So it turns out that I didn't know personally. I learned a lot from my different colleagues, in particular Jerry Marsden, that mechanics is actually geometry. I'm not going to try to explain this in all the gory details, but maybe it's worth still going through this Hamilton stationary action principle. I don't know how many people are aware of this, so I'm just going to explain with the hands. So don't expect that I'm being very mathematically correct, but I'm trying to get the notions across. So if you think about a mechanical system of any kind, you can think about what we call the configuration manifold, meaning all the positions, all the configurations that it can take. So then when you have your mechanical system, let's say this weird bunch of cubes with some smoke being blown at it, it starts at one point on the manifold, let's say at times t equals 0, and you know that you want to reach this location at times t equal big T. And the big question is, how does the system move? We know that it's moving on the manifold because it has to follow, has to be a configuration of your system, but you don't know which path. And Hamilton's was one of the first ones to say the right path is special in a geometric way. And this geometric way is simply that it's extremizing a score, if you want, which is the integral along this path of what is known as the Lagrangian. And the integral of the Lagrangian is called the action. That's why this is Hamilton's action principle. And so the physical path is one that will be a critical point of the action, meaning the integral of this Lagrangian. In mathematics, people write it like this. So this is a variation. You see the variation of this with 0 and t being fixed, because that's the extremities of your path, will have to be 0 so that the path is a critical point. So if you think about it naively, you could say, well, if I do the derivation, I found that the optimal way to get this action to be extremized is nothing but F equal ma. So what's the big deal? I was using before my Newtonian point of view. Why would I go to the Hamiltonian point of view? Well, it's very different in the sense that Hamilton thinks about physics in a boundary value problem, meaning that you really know the first point, you know the final point, and you give a description of the path in between. Whereas the Newtonian point of view was more of an initial value problem, meaning you know your configuration Q here, you know Q dot, meaning how the configuration was going towards, and then from this you guess where to go next. So you go one step at a time with no sort of memory of all the path before. Whereas the Hamilton's stationary action principle really says the whole path is optimal. So what's useful for this when you do numerics? Here's the idea. We can actually exactly use this geometric principle to create a time integrator. Let me explain how. First, we discretize things. So you know you're good at this. So instead of a continuous path on the configuration manifold, you look at a discrete path on the configuration manifold, right? So you discretize typically the time, right? So time stepping of your simulation. No problem there. So you start at Q0, then Q1, Q2, Q3, Q4, Q5. And then you ask, how do I turn this integral into something that I can actually compute from those samples? Well, guess what? You do quadrature, right? So for instance, you say the integral between two consecutive points qk and qk plus 1. This is the integral of the Lagrangian. I'm going to define it to be something. For instance, midpoint quadrature, right? That's one way to do quadrature of the integral thing. So you have now a discrete notion of action between 2 points. And then what you're going to do simply is you turn the integral into a sum. You're doing a reverse Leibniz, basically. So the integral turns into the sum of all these little actions. And now you realize something very simple and nice. If this point is qk, when I move qk on the configuration manifold, the whole path does not really change. The only thing that changes is the path between qk and qk minus 1 and qk and qk plus 1. That's the only two things that change, right? If you move just qk. And so that means that from qk and qk minus 1 and qk plus 1, you can say, okay, now let me fix qk minus 1, let me fix qk plus 1, and then I want to know what is the condition on qk so that the whole path between qk minus 1, qk plus 1 is optimal. And when you do this, you just do a derivation of this. You find a simple equation that you have to solve, which basically links these three terms. Once you have that, you're done. Because now, in a weird twist of the way you think about it, here I was thinking to derive it, I was thinking that qk minus 1 and qk plus 1 were fixed, and qk was the varying one. I got an equation. But now this equation It's basically a discrete Euler-Lagrange equation, if you want, of Hamilton's principle. Now this equation, I'm going to use it in reverse, meaning I'm going to suppose that qk minus 1 and qk is known, and I'm going to solve that equation to find qk plus 1. So I assume that qk plus 1 was known to get the equation on qk, but then this equation on qk is telling me what to solve to get qk plus 1 instead. And this, amazingly enough, has great properties. It can be shown to be symplectic, which means that basically the energy is very well preserved. There's plenty of symmetries, like, for instance, the momenta is preserved and everything. So there's lots of properties that can be derived from this. And it turns out that we had fun with this. We did a lot of Lie group integrators and integrators for cars, for helicopters. We even did molecular dynamics. Of course, it takes a little bit more time for molecular dynamics. But all of this with this idea of variational integrators that really follow the geometry of mechanics. So that was my point of view, is that even in mechanics, you can think of mechanics in a very geometric way. And more recently, over the last 5 or 6 years, because again of geometry, I got fascinated by this other methods that was started by Boltzmann, that basically, and I'm not going to talk about this today, but he thought about the configuration manifold in a very different way. But again, it's the geometry of the manifold that he considers differently. And the beautiful thing is that it creates a method that is neither the traditional macroscopic way where you solve for Navier-Stokes, pressure, blah, 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 nor the molecular dynamics, which would be way too slow to compute for fluids, but it has something in between that is called mesoscopic. I'm pointing you to a class that will, a course that we'll teach at SIGGRAPH this summer. If you want to know, you don't need to come to the course. The course notes will be online, so feel free to look at the courses. But the course notes. But the advantage is now for fluids, we can really do a lot of fun simulations, both for computer graphics and engineering. So we can do, for instance, surface tension problems like this paper boat on water. We can do stone skipping, where you can throw a stone and see it skip in water or not. So when my students does it, it does this. When I do it, it does this. It shows you my skills, but it's fun to see that it's exactly doing the right thing. We can even put water in a container and drop some more water. We see all the bubbles being formed and everything. And all of this in just a few seconds per frame. So compared to back in the days where it would take literally hours per frame, we came a long way. We can also do more on the engineering side. We can do virtual wind tunnels. So we were able to use some known examples of car designs and just run them through our own LBM-based, Lattice-Boltzmann method-based wind tunnel and get the results within 3%, like the industry wants, basically. So that's nice to see that even for engineering application, that works very nicely. And then this year at SIGGRAPH, we'll show how to mix sand with water. So here you have water dropping on top of sands, and then eventually the sand sort of separates from the bottom and just goes back to the surface to float, which was nice to have this sort of behavior captured in applications. Okay, so for the final vignette, that's going to be very fast, I wanted to show also how learning can be both interesting and annoying. I still like learning. There's plenty of things that I find annoying in the learning community, but I still like it. And so here's my take on learning based on the focus that I've had over the last 3 years. I was trying to say, how can we mesh a signed distance field? You all know about signed distance field. That's basically implicit function, but a particular one, which is just the signed distance to the surface. So let's say I give you a signed distance field, and I want a mesh of the surface that it represents. Okay, so as geometry processing people, you know that we can use marching cubes or dual contouring, solve problem, right? But then you start to think, well, marching cube and dual contouring is typically using piecewise linear interpolation between the values at the nodes, and that has to be not optimal. So basically, the mesh that you get out of marching cube, there's no way that's the optimal thing that you can get. And the idea is, hey, what about if I use data to sort of learn something better than a piecewise linear interpolation so that I can get a better mesh? And this fits in the whole 3D shape learning technology that people have been using thus far. So you can start from SDF or from a photo or anything, and then have a neural network, have a learnable 3D representation that sort of is optimized on your network, and then eventually return a shape, right? So here I'm going to talk only about the SDF case, but it could have been other types of input. And of course, you're going to train it on plenty of examples. Let's say, for instance, CAD shapes, if that's what you have available. And you can, after that, validate it on all the shapes that have nothing to do with CAD shapes so that nobody can argue that it's just learned overfit on your data, right? And so that's what we did. And we came up with so first of all, it turns out that there's plenty of learnable representations that exist. I created like 2, 4, 6, a family of 6 different representations that was valid 6 months ago. I'm sure by now there's 8, but that's the way it is. The problem is that if you compare to the baseline, which is the marching cubes, it has been improved into a neural marching cube, and dual contouring has been improved in the neural contouring. But for these 2 examples, 50% of the results are either not watertight or not manifold, sometimes neither. So as a geometry processing person, that hurts. I don't like this kind of lack of guarantees. And it turns out that the other extensions to marching cube type of methods don't fare much better. All these orange labels is where you cannot say, meaning sometimes you're lucky, it's good, sometimes you're not lucky, it's not good. And so this is annoying that you cannot guarantee lots of very basic notions for mesh extraction. And so what we did, I'm a little bit late, so I'm going to go very fast. What we did is to use, create a loss that we call the Voronoi loss, because it's basically used to create a Voronoi diagram. And we basically try to create a representation, a learnable model, where we have Voronoi sites inside and outside the shape, and we optimize the positions of these Voronoi sites so that the shape is best captured. So you start here on a regular grid, the nodes are on a regular grid, and then you make them move with this Voronoi loss. You optimize it so that it captures the shape. And once this technology is in place, what you can do is start learning from lots of sites how to directly go from the nodes on a regular grid close to your surface to where this Voronoi sites should go so that your shape is best approximated. So you learn this process instead of doing the minimization all the time for any new shape. You try to learn in one step how to get the Voronoi sites at the right locations. And so that's basically 2 neural networks, one to guess the position of the Voronoi sites, and one that guess the occupancy, meaning which Voronoi sites are inside, which one are outside. This one is the smallest network because you only have to guess plus or minus, basically. But then after that, once you learn on a bunch of meshes, then you can use it on any mesh and directly get, by extracting a subset of the Voronoi facets, you can extract a watertight and manifold representation of your mesh. And it turns out that on SDF that we tried, even complicated ones, we train it on CAD, and we, after that, evaluate it on non-CAD meshes. Of course, if it's fine enough, you really cannot tell much of the differences, but when it's very coarse, clearly the Voro mesh is actually much better and, of course, guaranteed to be watertight, etc. And then we did another version that's called Pong. I'm going to escape it, but it is basically the primal version. So instead of using Voronoi, we use more like Delaunay. And we mix it also with quadric matrices. And now it beats even Voromesh. So it does an even better job as Voromesh. So this is the state of the art as of 6 months ago. Compared to the ground truth, you see on this very coarse data, we get something that's decent. It's not perfect, of course, because it's super coarse data set, super coarse SDF, but it's much better than the other cases. And we show that it is on all the metrics, it is better. But then we thought to ourselves, okay, we have to come up with all this primal dual Voronoi cells, Voronoi sites, etc. It seems a little bit complicated. It was great because we were using computational geometry to do machine learning. So I loved it. But then at some point we said to ourselves, wait, the whole point was to try to say polynomial interpolation, like piecewise linear interpolation, is a little bit sad to be used on signed distance function. It's better to learn how to better interpolate. But why do we have to go through this learnable representation? In fact, what we can do is simply upres, meaning super resolve, if you want, the SDF. So if you have an SDF that is 32 by 32 by 32, well, then bring it in a machine learning way to 128 by 128 by 128. Then on this finer SDF, extract it with Logic Cube, and then you find you get a much better result. And that's actually the case. We will show a paper this year at SIGGRAPH that shows that, for instance, for a marching cube on a coarse grid data set, you get something where all the small tentacles are completely lost here. But if you use our super resolution SDF and then a marching cube on it, of course, you get something very close to the ground truth for at least for not only better results of all the other methods that I showed you, but actually even faster. So by bypassing completely the notion of learnable model, you actually get faster. So to me, that's an example where, okay, learning is great because it offers another way to think about the problem by learning from data. But sometimes we get into ways of doing things by habit, and then we discover that there's way simpler ways to go. So this is also what's interesting about learning. I think there's a lot of things to be changed to improve upon it. The good thing about this upresing is that we can do it also in animation. So if you have a low-res animation with very few frames, you can actually upres both in space and in time to get a simulation that is much more complex, obviously, because you appraise both the spatial resolution of your grid and also the temporal resolution of your simulation. And by the way, this simulation was appraised from the left simulation, but trained on just a ball flow, a flow around the ball. So that's really generality right there. It generalizes from this to this pretty easily with machine learning if you do it right. So this wraps up my talks. I wanted to show to you that computing through the lens of geometry can be quite useful, not only in low dimensions, but also in high dimensions. So I like to call this sometimes geometry-powered numerics. And what I really like is that it's blurring the line between discrete and differential treatments. So in fact, it's quite interesting sometimes to talk to mathematicians about, for instance, exterior calculus, etc. And they understand exactly what we're doing because, well, we're using the differential meaning just applied or at least adapted to the discrete setting in a sometimes straightforward, sometimes a little bit more complex way. And we are able to deal with nonlinearity in a interesting way, like, for instance, connection or very nonlinear things, right? If at school you learn about, what's the name of uh, these connections? Anyway, connections can be written by pen and paper in a very complex manner with lots of derivatives, etc. Of course, in the discrete world, we are able to do things that are much simpler, which doesn't mean that it's simple, but it's at least simpler. And of course, that will require, if you really want to enjoy the generality of geometry, that will require that you learn a lot of things about physics and exterior calculus, etc. And for the young people out there, you should learn about this either by going to class or ask an LLM now. Maybe it's just as fast. I don't know. I'm not young, so you'll have to decide. But you're at the age where you can learn all these things, so don't miss the boat because otherwise it becomes increasingly hard. And obviously, machine learning, I believe there's also much more to do on this topic. And on this, I wanted to thank all the people that I worked with. It's a wonderful thing to be old because you get to know a lot of former students, and some of them, for some reason, still want to work with you. So that's quite wonderful. So I want to acknowledge that most of the work that I've been talking about was actually done by other people. I just claimed that it's. Thank you so much. um, on the students or questions that there is most questions can be asked. So I'll just send you my microphone. And it's not just leave it there. We can that.
I started to see that war mentioned that is here maybe one line. How accurate geometrically what is the guarantee that you have the correct number of one pieces when you look at the mesh that exactly geometry.
So I'm sorry, I hear the sound really poorly from here. So I understood the question, but which part of the talk were you talking about? Oh, the neural mesh. Okay, the machine learning way. So what do you mean by accuracy? I mean, what people do is they look at the chamfer distance. So basically some weak form of Hausdorff distance between the reconstructed mesh and the ground truth mesh. So you start from a ground truth mesh, you compute on a regular grid of a given size the sign distance field. Then you give this to your machine learning algorithm, it outputs a mesh, and then you compare the output mesh to the ground truth.
Okay, sometimes you go um, exact
Right.
how you can correlate between the
So again, it's chamfer distance. I don't know if you're aware of it. It's basically samples and distances between the samples. So because it's differentiable, so people have used this chamfer distance. Otherwise, you can even evaluate the Hausdorff distance. It's okay. You can do whatever metric you want. For some reason that makes sense because it's easier to evaluate. People use chamfer distance. I don't know if you know about it. And so that's what we do. But visually, it's clear that it's a better mesh. After that, obviously, depending on the metric, the notion of better is really strong or a little bit weak.
thank you very well. I was maybe very genuine question about discretizations. You've talked a lot of it, and of course there was geometry discretization in space, but there is also discretization in time and so on.
Yeah, the
I
mechanics.
was for me about your experience in protein dynamics, talking about that. Because here discretization is really challenging. These dynamics, protein sometimes the vibrate for a long time in some space, and suddenly from such the jump to another mega stuff. Here, discretization, if you compare the time between this and the time of these jumps, it's 1 to 10 to the power 6. So how do you remember if you experiment about this changing in the scales of this discretization before that and you will never get there?
So I have zero experience on this. What we did in the molecular dynamics case, we took the simulation of DNA and the ligands, whatever they call it, linking the two strands of DNA. And people were doing this with a particular integration method. And we said, okay, we can rewrite this as a symplectic method with, long story short, with exponential of matrices, etc., so that the time step that we could take was something like 80 times larger. So we got a speed up not of 80 because we use exponential of matrices. So I think we got a speed up of 20 or 40. But I've never really tried on proteins and this problem of having to compute for a long time before it jumps. So I have nothing to say about the exact question you're asking. We just use molecular dynamics to prove that if you use a symplectic integrator with some bells and whistles to make it uh, able to do bigger time steps, it works and give the right result just faster. It does not answer your question at all, and I have no clue. Okay. By the way, I would be extreme. I mean, people are already doing this, but I'm guessing that machine learning has to play a role in this because detecting this kind of big jumps seems like at least they could pre-chew the computations for you. Right, right. Absolutely. Thank you. Yes. No, the vector field. You're right. So I went very fast. Obviously, that was just to say you don't need to do appraising just of the SDF. You can do other type of appraising. So you're absolutely right. What we learn here is how to appraise the velocity field. And the idea is, the velocity field is satisfying Navier-Stokes. So again, Navier-Stokes is a local condition, right? And so our point of view, at least in this work, was to say, because it's local, that has to be true everywhere. And so we can try to take a small window, typically 5 by 5 by 5 or 8 by 8 by 8 of grid nodes with the velocities on these grid nodes, force grid nodes, and then try to learn how to appraise it to a finer uh, simulation. And so that's what we did here. We use actually a dictionary-based appraising, which is very different from the previous method. The previous method, we said we want it fast, and we don't really care. There's no physics, right? So we don't really care about the accuracy. We just want an appraising that's really fast. Here, we cared more about the physics, so we did actually a little bit slower using a dictionary-based learning, L1 minimization, etc. But entirely by learning how to appraise a little chunk of velocity vectors from a coarse grid to a fine grid. And then once you have that, you can use it on any big grid because you're going to use the same little network to learn how to appraise locally the vector field that you're dealing with. Thank you.